Good day, everyone. We are the pair number 1 from Group 4, BSECE1A, and I am Joel Mark Alalguna together with Jefferson Baldestamon, and we will be talking about reciprocal leveling and the trigonometric leveling. So, let's proceed to the reciprocal leveling. Reciprocal leveling is a type of surveying method or surveying technique that is used to determine the elevation between 2 points when it's impossible to set up a leveling instrument midway between them. Like, it can be useful and when you are using it in like rivers, lakes, valleys, ravines, and that kind of stuff. It helps reduce errors from refraction and curvature, as well as instrument misadjustments. It can also, it is involved in setting up the leveling instrument near one point and taking readings on stuff held on the other point. This method, as I've said, helps to eliminate errors caused by instrument maladjustments or misadjustments, earth curvature, and atmospheric refraction. So let's proceed to the procedure and how you do this method. In the first setup, you have to set up the level near point A and take the staff reading from points A to B. And then you have to move the level and set up to another point B. Then take staff readings at points A and B. Then you have to calculate it. The formula for that is DE is equals to A minus B, and it's the same also in the second setup, just of course different in values because it's elevated higher. Once you calculate those, after you compute DE equals A minus B, you have to add the answer, then divide it by 2, and then you get your leveling setup. Okay, so the importance of this leveling method is it can eliminate errors from curvature, refraction, and instrument maladjustments. It can ensure the accuracy across long or rough distances, and it is also useful for engineering projects near rivers, bridges, large obstacles, valleys, valleys and ravines. Also, on obtaining more accurate measurements, atmospheric condition that affects accuracy, observe them when temperature is stable. And when you're making observation, it is preferably that you do it on cloudy days or the middle of noon, so that the temperature doesn't rise as faster as it should. Then you have to use instruments and you have to take multiple readings to ensure that the one that you took, like example 99 example where you get 99, then you took another test, then it took 98 point something, and then you put it again, and then 99.3. So therefore you can conclude na sakto gid man ang imong measurement, which is 99, right? So next, interchange rods and repeat measurements to minimize errors. Okay, next, conclusion. So we can conclude that reciprocal leveling is a precise method to measure elevation difference across obstacles or uneven terrain by averaging readings from both sides. It compensates for errors and achieves accuracy similar to differential leveling. And for its applications, it is much more used in construction and surveying, of course, and of course para ma-determine mo elevations and benchmarks and reference points. And in construction naman, it is used to establish levels of different points on site and to ensure that there is proper alignment and grading. That's all for reciprocal leveling. Thank you.
Hi sir, my name is Jefferson Baldestamon and I'm going to talk about trigonometric leveling. Sir, trigonometric leveling is a leveling method used to find the difference or the elevation difference of two far or inaccessible points using angles and distances. This concept is based on forming a right triangle from the instrument to the target. With this, we measured the horizontal distance, vertical angle, its instrumental height, and the target height. Now, for finding the vertical height, we are going to use the most basic formula, which is vertical height is equals to d tangent theta, or the horizontal distance multiplied to the tangent of the vertical angle. Whereas, the, if the angle is positive, point P is higher. And if it is negative, point P is lower. Now, its full formula is the elevation of point B is equals to the elevation of point A plus its instrumental height plus minus the vertical height or d tangent theta minus its target height. This method is very useful when you encounter steep terrains, long distances, or when direct leveling is not possible. Now, sir, that is trigonometric leveling.
Good day, everyone. This is Pair 2 from Group 4. I am Juan Miguel Blanca along with Jesse J. Halandra, and today we will be discussing Lesson 22 Barometric Leveling. So, what is barometric leveling? It is all about using atmospheric pressure to determine elevation. Instead of using traditional leveling tools, we use instruments like barometers and altimeters. These tools help us understand how high or low a location is by detecting changes in the air pressure around us. Now, the core idea of barometric leveling is simple. Air pressure decreases as elevation increases. At lower elevations, the air is dense, so pressure is higher. At higher elevation, the air is thinner, so pressure is lower. Barometers measure these pressure changes. By comparing readings, we can estimate elevation differences. Now, the primary tool, which is the barometer. There are two main types of barometers used. Number one is the mercury barometer. It is highly accurate but bulky. It uses a column of mercury to balance atmospheric pressure, and the height of the mercury column reflects the pressure. Number two is the aneroid barometer. It's portable and mechanical. It uses a sealed metal capsule that expands or contracts with pressure changes. These movements are translated into readings on a dial. Now, there's a specialized tool called the surveying altimeter. Surveying altimeters are a specialized type of aneroid barometer. The key difference is that the scale is calibrated to show elevation directly, not just pressure. This makes them ideal for quick topographic surveys and reconnaissance work, especially in remote areas.
The biggest enemy of barometric leveling is the weather. A change in temperature or a shift in barometric pressure affects every reading. We treat the weather like system error. To isolate and remove this error, we use the two instrument simultaneous measurement method. We establish a base station. This is an instrument placed at a location where the elevation is already known. Its job is not to measure the field point but to act as a control. It continuously records any pressure caused purely by atmospheric events, like a sudden shift in wind or temperature. Meanwhile, the second instrument, the field station, is moved around the site to measure all the unknown elevations. And the final step or the crucial step is the correction. Readings are taken at the exact same time at both stations. Because the weather effects are simultaneous at both the base and the field station, we can simply subtract the changes recorded at the base station from the reading at the field station. This cancels out the effect of the weather, leaving us with an accurate measurement of the elevation difference between the two points. Then we go on to the barometric formula. The barometric equation is fundamentally a description of how pressure changes with depth in a gas. In air, the density is not constant. It decreases as you go up, and this decrease is exponential. The formula for pressure is P is equals to the P0, which is the pressure at sea level, times the base of the natural logarithm e to the power of negative mass times gravity times height divided by the Boltzmann constant times temperature. This exponential drop-off is driven by a fundamental competition in the atmosphere, represented by the ratio with the exponent, gravitational potential energy, or the MGH. This is the energy pulling the air molecules down towards the Earth's surface. And the opposing force is the thermal energy, which is the Boltzmann constant times temperature. This is the average kinetic energy of the molecules, which causes them to move around and spread outwards. This formula essentially states that the pressure at any height is dependent on the starting pressure and the decay based on this ratio of energy that determines the probability of finding an air molecules at that specific altitude. When we rearrange the formula to solve for the height, we get the H is equal to negative Boltzmann constant times temperature divided by the mass times gravity times natural logarithmic ln p or pressure times pressure at the sea level. The natural logarithm ln is a necessary mathematical function to invert that exponential decay curve, enabling us to translate the measured pressure ratio, pressure divided by pressure at the sea level, into a precise vertical distance. Then we move on to the inverse leveling. Standard surveying requires an uninterrupted path, but in the field we often encounter obstacles that prevent us from setting up instruments directly, like a wide canyon or a deep chasm. In this case, we employ inverse leveling. This technique involves using trigonometric principle and specialized optical or pressure correction to transfer the elevation line across the barrier. Think of it as shooting a precise imaginary line over the gap to maintain the integrity of a survey when physical access is denied. To wrap up, barometric leveling is highly valued in engineering and geography for two key reasons. It's incredibly fast and very cost effective compared to the traditional methods. However, its critical limitation is that it's less accurate than high precision geometric leveling. Therefore, we define its best applications. First is preliminary survey, getting a fast and general lay of the land before committing time and resources to detailed work. Then we have the reconnaissance and mapping remote areas, covering vast territories quickly where the cost of achieving extreme accuracy outweighs the benefit. It is a versatile tool for defining the macro topology of a site, providing essential data for project planning. And that is all for the barometric leveling.
Good day, everyone. My name is Fritz Isabel Goloso together with Vince Paulo Bennett. And today I will be discussing cross-section leveling, which is a method used in surveying to obtain short profiles perpendicular to the center line of projects such as highways, railroads, sewer lines, and other construction works. Okay, so cross sections are short profiles taken perpendicular to the center line of objects such as highways, railways, and sewer lines. They provide necessary information for estimating quantities of earthwork, which is the process of reshaping the ground for construction. These cross-sections are also important for planning excavations such as barrow pits and for determining the ground's natural shape, which is needed for constructing stable building supports. There are two main types of cross sections, and the first type is roadway cross sections. These are commonly used in route projects like roads and railroads. In this method, cross sections are taken at regular intervals such as 5, 10, 15, or 20 meters, and additional sections are taken at full stations, plus stations, and areas where there are abrupt changes in the ground. Each cross-section must extend far enough from the center line to cover the right-of-way or any area where earthquake may occur, and elevations are recorded at points where the ground changes significantly. Recording the data for cross-sectional leveling follows a method similar to profile leveling. First, the height of instrument or HI is determined by taking a backside on a benchmark or any point with a known elevation. To accurately represent the ground shape, rod readings are taken at several points along the cross sections. The distance of each ground point from the center line is measured using a steel tape, while the elevations of these points are calculated to the nearest decimeter. Benchmarks and turning points, however, are noted more precisely to the nearest centimeter. The recording system is divided into two pages. On the left-hand page, the surveyor writes the reading on benchmarks, turning points, heights of instrument, and elevation of stations. On the right-hand page, all cross-section data are recorded. A line is drawn down the middle of the page to represent the center line. Any rod reading taken to the left of the center line is recorded on the left side of this line, while readings taken to the right are written on the right. Field notes are written in fraction form. The numerator represents the rod reading, and the denominator represents the distance of the point from the center line. Once the data is collected, graph paper is used to plot elevations and visualize the ground profile. A planimeter may then be used to determine the areas of the plotted cross-sections, which will later use to compute volumes. The second type of cross-sections is barrow pit cross-sections, which are usually found adjacent to a construction site. In this method, the area is divided into grid system made up of squares or rectangles marked by letters and numbers. The intersecting points of the grid are placed close enough so that the ground slopes between them are approximately uniform. At the site, temporary stakes are placed at each grid corner, and the transit and the tape are used for measurement. Elevations are taken at each grid corner both before and after excavation. These two sets of elevations are then compared to determine the volume of the material excavated. Here is the example or illustration of the two types of cross-section leveling.
I am Vince Paulo Bennett, and I will discuss the adjustment of level circuit. It is also known as a loop. It is a line of leveling that begins and ends at the same point, or runs between 2 points whose elevations are precisely known. The purpose of a level circuit is to check for and correct the errors that naturally occur during leveling. Because no measurement is perfect, the computed elevation at the ending point often does not match the known elevation. This difference is called the error of closure. The error of closure is calculated by subtracting the known elevation from the observed elevation. In order to correct this error and ensure the accuracy of the leveling work, a correction is applied to each point in the level circuit. This correction is computed in proportion to the distance of each point from the starting benchmark. If the error of closure is negative, the corrections are added to the observed elevations. If positive, the corrections are subtracted. Next, there are two main methods of adjusting level circuits. First is levels over one route, which is used when the points lie along a single path. In this method, the correction applied to each point is proportional to its distance from the starting point. This approach is used when all points are close enough to be seen from a single instrument setup, making it useful for quickly determining elevations in a small area. If the distances are unknown, corrections may be distributed proportionally to the number of setups made by the instrument. Second method is levels over different routes. It is used when several leveling lines extend from the same origin to the same endpoint. Because each route provides a different observed elevation, the results must be combined using weighted values. The weight of each route is inversely proportional to its length, meaning shorter routes are given more weight because they are considered more accurate. After applying these weights, a final adjusted elevation is computed.
In summary, cross-section leveling is an essential surveying technique used to study the ground surface in construction projects. By taking measurements perpendicular to the center line, engineers can estimate earthwork quantities, plan excavations, and design features like roadways and barrow pits. Proper recording methods, including rod readings, field notes, and plotting, ensure accurate representation of the land. Adjustment of level circuits is equally important because leveling measurements are prone to error. Surveyors must calculate the error of closure and distribute corrections to ensure accuracy, whether using a single route or multiple routes. These corrections allow engineers to obtain reliable elevation data, which is crucial for safe and accurate construction planning. This is all. Once again, I am Fritz Isabel Galoso together with Vince Paulo Bennett, and we hope that you have learned a lot today. Thank you.